realize and then hit record. What your graph is doing here is actually shows as though these curves are touching the x-axis, but actually it should not be touching right over here. So if you have that horizontal axis, your curve should be getting really close to it, but there should be no contact between the curve and the horizontal axis. And you can see they actually do a better job of that in your handouts, because you will see how there's that little gap between the curve and the horizontal axis, because that's what's happening over here is your graph is getting really, really close to the x-axis, but like they're telling you here, it never reaches the horizontal axis. It just gets really close to it, but it will never reach it. And that's because of that horizontal asymptote that I was talking about. So just something to kind of think about, as you're going through these sections, okay? They're also listing pretty much those same properties over here. So you can, again, read those here in your handout as well. Now, since you guys are familiar with the empirical rule, we have talked about this before. So we know from the center where you have your mean, which is right over here, if you go 1 standard deviation below and 1 standard deviation above, so that would be this area over here. This is going to add up to, approximately 68%, or you can see the exact value would be 68.26. If you go 2 standard deviations away from the mean, so start at the mean and go 2 standard deviations below and 2 standard deviations above. So that would be everything in the middle, and then this area from 2 and 2. That comes out to be approximately 95%. And then if I go from the mean again, so right from the center, I go 3 standard deviations below, and I go 3 standard deviations above the mean. So that would be everything in the middle, and then going 3 standard deviations out in either direction. That actually comes out to be 99.7% of, that total 100% or that total 1 value in there. But what you should notice at that point is that you still have a little bit of this tail area left. So let's get rid of this for now. So that little bit of the tail area, which is on either side, once you get out to 3 standard deviations from your mean. Okay, better. So, and you know what, let's make this guy a little bit bigger. So we're talking about after 3 standard deviations, this little area over here and this little area over here. So we know everything in between, going from this mark to this mark, all of this in the middle, this is coming out to be 99.7. So we know we are shy of 100%. So if you subtract this number from 100%, approximately, you are looking at, what will that be? 0.3%. And that's going to be for both of the tails. So divide that by 2, and you will get 0.15%. Exact number you will see actually comes out to be 0.13 and 0.13 if we take all of these decimals into play. But if you go with approximately 99.7 for 3 standard deviations, then those tails come out to be approximately 0.15. So you can see a little bit, of those tails, and then everything put together comes out to be 100%. So that's kind of how we define these areas or probabilities beneath a bell-shaped curve. And we use this idea of the area and convert it into probabilities. And you'll see different examples of that, in your homework and your handout and textbook. So this, like I said, is going to be a symmetric, distribution or a symmetric curve. And in symmetry, and again, I know this is going to be a little bit blurry because these images were really small, but in a bell-shaped curve, which is right here in the blue, your mean, median, mode are all the same value, so they fall right in the center. But if you have a negatively skewed distribution, so it's not bell-shaped, it's negatively skewed, which means you have a tail only on the left-hand side, you will see your mean is the leftmost value. So mean, then median in the middle, and mode is to the right. So they are all different values, and you can see in what order they fall. If you have a positively skewed, or your tail is going to be on the right hand side, then in this case your mode is actually closer to where that um, center peak is. And then you have again median in the middle, and then mean now comes out to the right. So you can see, guys, where you have the tail, your mean is going to be closer to the tail area. So look at that left skewed or right skewed. Wherever that tail is, your mean is closer to the tail. And then wherever the peak is in those bottom two graphs, closer towards the peak is your mode. And then in the bell-shaped curve, of course, all three of them are going to be in the same position. So just to show you, just that little bit of a difference, why normal distribution is the way it is, and the other distributions are going to look very different from that. So when you are working with bell curves or normal distribution, we actually always want to convert our data values to whatever it's given in your example to a standard normal distribution. Because, we can say the average height for adult women in the US is, I don't know, and I had used this number last time, I think 5 feet 7 inches or something like that. And I'm just making this number up. I honestly don't know what it is. So, if you have 5 feet 7 inches, well, that's for one example, right? And we can say the standard deviation is 2 inches. And then you can create your bell curve based on that. But then what if we want to change that example and we want to say the average height for men is 5 feet 10 inches with a standard deviation of 3 inches? Well, then we will not be able to use the bell curve we designed for the adult height of women. Now we will have to create a whole new bell curve for the adult height of men. So that's the reason why, if we can just take these mean and standard deviations for these different groups you're looking at and convert it to a standard normal distribution, then that means your mean will still fall in the center, but now it will be a value of 0. If you are going one standard deviation out from the mean, that's +1 and -1, above or below the mean. You can do 2 standard deviations above and below, 3 standard deviations above and below. And then, of course, we can use these same percentages that we have in the, we looked at over here, and you will see those are the same percentages we're describing over here. So take, whatever example you have, whatever values you have, and convert them to a standard normal distribution. And to do that, you use this formula, which again, you have seen in that chapter 3, where they called it the standard score or the z-score. So you take your data value, subtract the mean from it, and divide it by standard deviation, and you get your z-score, which you will now be able to use in the standard normal distribution. And it actually comes with this table. So based on the z-score that you have, it can be a negative number if the value is smaller than the mean, or it can be a positive number if your value is greater than the mean. Because, right here where you're subtracting the value from the mean, if this value is going to be smaller than the mean, your z-score will be negative. If the value is going to be larger than the mean, then your z-score is going to be positive. And then, based on that, you can use this table to calculate your, area or probability or percentage, whatever you are looking at. So they actually walk you through the different steps depending on, which area you are looking for. Is it a value underneath or less than the z-score? Is it a value greater than the z-score? Or if it's going to be sandwiched between 2 z-scores, based on that, we can try and calculate that. So let's take a look at an example. You know what, let's see if we can find something in your textbook here. I was hoping to do. Let's do this one over here with the refrigerators. Okay, Elijah, I just saw your message, and I'm really sorry about that. I hope the internet will start working a little bit better. All right, guys. So this.
It's already kicked me out like 3 times, I think.
Oh,
So
wow.
yeah, if I keep leaving, that is why. What's going on?
Okay. Yeah, and unfortunately, we have no control over, what your internet provider is gonna do. Some days are just, yeah, they don't work out the way you want them to. So let's see how we can apply this idea of, taking an application and converting the information they're giving us from what's given to us into a standard normal distribution, and then how can we use that normal curve to help us out. So they're telling us the lives of refrigerators are normally distributed. And remember, with examples like these, guys, they have to tell you that it's a normally distributed variable, right? We cannot make the assumption something is normally distributed. So if they don't tell you that this is normally distributed, you cannot use normal distribution for it. Then you have to go and use Chebyshev's theorem, which is what you saw in chapter 3. But when they specifically tell you it is normally distributed, then we are good to go. They're telling us the lives of refrigerators are normally distributed with a mean of 14 years and a standard deviation of 2.5 years. So they're asking us to draw a normal curve with the parameters labeled. Shade the region that represents the proportion of refrigerators that will last more than 17 years. So they're telling us the mean life of a refrigerator is 14 years, but they want to know, what that area would look like if it's going to be more than 17 years. And they're saying, suppose that the area under the normal curve to the right of x equals 17 is 0.1151. Provide two interpretations of this result. So we'll get to that, in a minute. But let's go ahead and do the first parts of these. So I'm actually going to transfer this information over here to our notebook. So number 32, refrigerators. So the mean life is 14 years. Standard deviation is 2.5 years. So let's do a bell curve first, based on this. So we have our horizontal axis. We'll do, our bell curve. Again, remember those edges don't touch the horizontal axis. And I'm just doing a basic shape over here. So, right in the center is where we have our mean. Then you go out one standard deviation above, one standard deviation after that, and one more after that. Same thing on the lower side, one standard deviation below, two standard deviations below, and three standard deviations below. So they are telling us the mean is 14 years. So this centermost value is going to be 14. Then your standard deviation is 2.5 years. So that means you are taking 14 and adding 2.5 to that to get your first standard deviation. So what will that give us, guys? 14 plus 2.5.
16.5?
Yeah, 16.5. So that means, refrigerators that have a life of 16.5s, all of those will go on the right-hand side. So keep adding 2.5 to that. So you can either take 16.5 and add another 2.5 to it, or you can do 14 plus 2 times 2.5, for your second standard deviation, which would still give you the same answer. So that would be what? 17, 18, 19. So this should be 19 years over here. And then for the 3 standard deviations, you can again take 19 and add 2.5 to that, or you can do 14 plus 3 times 2.5. So what do you think that third standard deviation above the mean will look like?
21.5.
Yeah, 21.5, very good. And in that same way, you will start doing below the mean. So for below the mean, you will take 14 and this time subtract 2.5 from it. So what will that give us?
11.5.
Very good. 11.5 for one below the mean. And same thing, you can do 14 minus 2 times 2.5, or you can do 11.5 minus 2.5, and that will give you 2 standard deviations below the mean.
9.
Very good. 9. And then for 3 standard deviations below,
6.5.
very good. Alrighty, so these will be the values, based on this particular example. Now, if we needed to change this to our standard normal distribution, then remember your mean is always going to be 0. This would be 1, 2, 3. This would be -1, -2, -3. So, of course, it corresponds with those standard deviations, 1 or 2 below the mean, above the mean, that kind of thing. Now, in the second part of this problem, they were saying, shade the region that represents the proportion of refrigerators that last more than 17 years. So you can see at 16.5, you are at 1 standard deviation above the mean. So your 17 is going to be somewhere closer to that, because 2 standard deviation puts us as 19 years, and we're obviously not quite at 19 years. So I'm just going to eyeball this, but let's say somewhere over here is going to be our 17 years. I guess I'm just going to use an arrow, and this is for 17. And they want to know the refrigerators that last more than 17, which means it's actually going to be this area till you get to that tail at the end, right? So this is going to be the shaded region that we are basically interested in. How many refrigerators? So this can be in terms of how many refrigerators. This can be in terms of what's the probability that a refrigerator will last, more than 17 years. I mean, you can have different types of questions, based on these types of examples. Now they are saying, suppose the area under the normal curve to the right of x equals 17 is 0.1151. So this shade area that we shaded, they are saying, suppose this area is 0.1151. Well, what exactly does that mean? So this is kind of what, your bell curve helps you do. Now we'll look at how to come up with these numbers. Right now, they're just familiarizing you with the normal distribution. So the idea is you can look at 0.1151 and you can say the probability that your refrigerator will last more than 17 years is approximately 0.1151, or we can say approximately 11.51%. So, shading this was part B. And then for part C, we can say, the probability that your refrigerator will last more than 7 years is 0.1151. So we can look at this as a probability. We can also look at this as a percentage, and we can say So, how many ever refrigerators this manufacturer or, whoever is making them has, we can say about 11.5% of those refrigerators will last more than 17 years. So you can see many of them are obviously not going to have a life cycle of 17 years or longer than that. You have a pretty small percentage of refrigerators. So different ways that you can kind of look at that area under the curve and use that for answering your questions. And that's kind of what these you explain it questions that they have over here is kind of having you do that explanation part. But let's see if we can find, because most of these are actually giving you the area. So yeah, let's get into our next section because this is where they will actually help us doing calculations. So let's take a look at, I actually did want to do some of these generic questions. You know what? Let's do these since your textbook is not showing us this example. Let's take a look at this. So once you have your, and we're just using the standard normal curve over here for now, but we want to know what is the area between 0 and 2.53. So 0, of course, is where your mean is going to be. And 2.53 basically means you are between second standard deviation and third standard deviation above the mean. So, you're kind of halfway between that. So for 2.53, and if I just had to show you that on this curve, it's going to be basically right here, halfway between +2 and +3 on our normal curve. So, that's kind of what this one over here is. So this is the area that we are interested in finding. So what you actually have to do is, since they're giving you that z-score of 2.53, you actually go to your standard normal distribution table and you have to find out where exactly that 2.53 is going to be. So 2.5 is what you are going to be looking at on the left-hand side of this table. So there's your 2.5. And remember, your z-score is 2.53. So this actually breaks down into 2.5 for that first part. Since this is your second decimal place, that becomes 0.03. So 2.5 on the left-hand side, and then 0.03, you have to look for that on the top row. So you can see right here is 0.03. So where those two rows and columns meet is where you will find that area. So you can see 2.5 and 0.03 are going to meet right here at this place. And that is telling you this area is 0.9943. So what that actually means, where you have 0.9943, that actually means it's going from here all the way till the bottom tail end of your bell curve. So it's all of this area together, which is 0.9943. However, we are not interested in, all the way till the bottom or to the left-hand side of our curve. We want to stop at 0. So this is where that idea of symmetry and the left half being 0.5 or half and the right half being 0.5 and half comes into play. So since we are not interested in this area over here, this is the bottom half of your normal curve, you actually subtract 0.5 from it, and you can see that calculation right over here. They're just putting extra zeros at the end. Subtract the 2 and you end up getting 4943, which is actually this shaded part. That's the area for that shaded portion. And you can again think of that as a probability or as a percentage. So we can say, whatever this example might be referring to, the chance that this will happen is 49.43% or a probability of 0.4943. So you end up subtracting, that 50% for the bottom half, which we were not including in our shaded area. In the second example, they just want to know, what is the probability for a z-score of less than 1.73. So you can see less than 1.73. It wasn't between 0 and that number like you had in part A, right? This was between 0 and 2.53, but this guy is just saying less than 1.73. So when it says less than, that means you are going all the way till that left tail. So if you look at 1.73, so, again, we will do 1.7 on the left. The 3 will come on the top, just like you did in the previous example, and then find where these two lines meet. And you will see this guy comes out to be 9582. So this entire area where you have the 1.73 and all the way to the left, all of this is shaded. So that together, makes up your 0.9582 or a chance of 95.82%. So less than is literally straightforward because you just look at the table, whatever area you get, that's it. But if it's going to be sandwiched between two numbers, then we have to do subtraction, or if they give you a greater than, which means greater than, you are looking at this area on the right-hand side. So what is the probability for a Z value being greater than 1.98? So for this area, what we would have to do is, again, look for 1.98 in your table. So 1.9 is right over here at the bottom, 1.9, and you will see the 8 is right over here. So 1.98 will bring us to this little portion, 0.9761. So remember, 0.9761 is actually for this region here, which was not even shaded, because that's how your standard normal distribution table works. And you can see these graphs over here, they always give you the area shaded to the left. And you can see that on both pages of this normal distribution table. They always by default give you the area on the left. That's the reason why in part B, you didn't have to do any calculation. You just got the number off the table and you were good to go. But because in part C, they're giving you the area greater than, and the table by default gives you the area to the left, this was the area which was that 0.9761. Well, I'm interested on the area to the right-hand side. So that's why we know the entire bell curve has an area of 1. So from 1, and again, you can make it into decimals by putting zeros at the end. You subtract this area we found out, 9761, and you end up getting 0.0239, which is approximately 2.39%. So depending on where that shaded part of your bell curve is going to be, we are going to have to interpret and do calculations to see, do we leave the number as it is? Do we need to, subtract it from two different numbers, or, what kind of calculation you need to do? So in this first handout, you do have a lot of these generic examples where you are given the Z-score and they're just asking you to find the area. So that may be something that, you want to kind of look through and just get familiar with. But then when you get into the second, and that's again, section 7.2 is where we get into the applications. This is where we will have to use our little Z-score or standard score formula to convert our values to find the Z-score, and then we can solve the different applications. So let's take a look at an example over here. This is already less than. Let's find something in between. Yeah, I like this one. So let's take a look at this example here. This one is saying, each month, an American household generates an average of 28 pounds of newspaper for garbage or recycling. Assume that the variable is approximately normally distributed. Remember what I said, this terminology has to be there for us to do these examples. And they're telling us the standard deviation is 2 pounds. So your average, of course, in this case would be the mean. Standard deviation, they're telling us it's approximately normally distributed, and they're saying if a household is selected at random, find the probability that the household is generating between 27 to 31 pounds of newspaper per month, or more than 30 pounds of newspaper per month. So the first thing you do is start out with your normal curve and where you're going to shade this. So let me actually show that to you over here. Okay, so we know they have an average of 28 pounds. This is example 2. So average of 28 pounds. They're telling us a standard deviation of 2 pounds. And for part A, they wanted to know it's going to be between 27 and 31 pounds of newspaper per month. Okay. So if we draw a bell curve based on this, again, just a general shape over here. Right, your mean is going to be right in the center. And I'm actually going to do this with our standard curve and then, bring in our values for this particular example. So our mean is at 28 pounds, just like we did in the previous example. So based on this one, we know our, come on, buddy, is at 28 pounds. 2 pounds of standard deviation. So of course, if we go 1 standard deviation above, that would be 28 plus 2, which would put us at 30. 30 plus 2 would be 32. 32 plus 2 would be 34. So, we keep adding that standard deviation of 2 pounds to get our 3 standard deviations above. And then to get your standard deviations below, we will subtract. So 28 minus 2 will give us 26. 26 minus 2 will give us 24. 24 minus 2 will give us 22. So these numbers are in particular to our example. And then they told us between 27 and 31. So you can see 27 is less than our mean. It's going to be right here in the middle of 26 and 28. So 27 is going to be right here. 31, as you can see, again, is going to be between 30 and 32. So halfway between 1 and 2 standard deviation. So this is the area we are looking at. So it goes below the mean and it goes above the mean. So the first thing we would have to do before we can even go to that standard normal distribution table is we will have to find the z-scores for 27 and 31. So this is where, we are converting this from just a regular application into a standard normal distribution application. So let's start with that. We'll find the z-score for 27, and we'll find the z-score for 31. So remember your formula for z-score was data value minus the mean divided by standard deviation. So your data value is 27. Your mean is 28. Divide that by your standard deviation. Same thing for 31. Minus 28 divided by 2. So can you tell me what our 2 z-scores come out to be when you do these little calculations? If it's below the mean, it should be negative. If it's above the mean, it should be positive.
I came up with negative 0.5 for z-score of 27.
Okay, yeah, because 27 minus 28 will give you negative 1, and then you're dividing it by 2. Did you say 25?
Negative 0.5.
0.5, there we go. Yeah, because you get negative 1/2 as that fraction, which as a decimal would be negative 0.5. Okay, very good. So negative was expected because 27 is a number smaller than 28. And then what did you get your z-score for 31, guys?
For the second one, I got 1.5.
Yeah, and if you look at our bell curve, these numbers were expected because look at where our 27 fell. Your 27 is right here between well, not what I wanted to do, but I know you can't see the line for that 0 in there, but look at where 27 falls. It's right between where our mean was. Oh, buddy, come on. Right here. Halfway between 0 and -1. So yeah, it was expected it was going to be negative 0.5. And then look at where 31 falls. 31 is right between 1 standard deviation and 2 standard deviations. So again, right there between 1 and 2. So that was again expected to be 1.5. And that's why, you know, I like using the standard normal distribution, because you can look at the normal curve and, you know, at least for numbers as simple as these, you can find out where those standard deviations are going to be. All right, so once we find these standard deviations, now we need to find what their areas are going to be. So let's start with negative 0.5. So for this guy, we will need to go back to our table over here, and this time we're on the negative side. So again, it's negative 0.5. And you will see right here is our negative 0.5. Now you have no other number next to it, so you know we can assume there's a 0 after that 5. So negative 0.5 on the left, and then on the top, you will actually just be at 0, 0, because you know we didn't have any other numbers after the 5. So where the two of them meet will give us our area for that first number. So 0.3085. So this guy is 0.3085. Now remember how this table works. Your 0.3085 is technically starting at 27, and then remember it goes below, right? So this is actually the area, which is your 0.3085. Now for our second z-score, 1.5, we will go back to our table. 1.5, so that's on the positive side of the table. And here's your 1.5. And again, you will see there's no decimal after that. So again, you can assume there's a 0 next to it. So 1.5, and then again, just go with 0, 0 on the top column. So 1.5 and 0, 0 meets right here at 0.9332. 0.9332. So remember this area here, and I guess we'll use this color, is actually going from where 31 starts and, you know, all the way till the tail. So it's actually this area that you are looking at as the 0.9932. So remember, we're interested in that green area, right? We don't want the yellow. We definitely don't want all of this orange, which would be, you know, everything yellow and green put together. So this is again where, because your area that you are looking at is sandwiched between two numbers, to calculate your final area or probability, we would say, what's the probability that our X value is going to be between 27 and 31, which actually translates as what's our probability that it will be between negative 0.5 for our z-score and 1.5 for the other z-score. So here's your data value with the X, 27 and 31. When we converted that into standard normal distribution, the X changes to a z-score. 27 became negative 0.5, 31 became 1.5, and this probability is where we take the larger area, 0.9332, and from that we subtract the smaller area of 0.3085, and that will give us that green shaded area that we were looking for. And of course, you have this calculation already done for us, but just to verify it, this comes out to be 0.6247. So this is your probability. Or as a percentage, this would be 62.47%. So we can say about so they said if a household was selected at random, what's the probability that they are generating 27.31? So we can say approximately the chances that a randomly selected household is generating 27 to 31 pounds of newspaper for recycling or garbage is 62.47%. That's a very likely happening, right? Because it's more than 50%. So we can say, yeah, there's a good chance that if you randomly select a house, they are generating anywhere between 27 to 31 pounds of, garbage, basically, with newspapers. So that was, if you're in between two numbers. Now with that more than 30.2 pounds, if you had to do that calculation, more than, oh, stop. More than 30.2 pounds. Well, again, you can see 30 pounds was at one standard deviation. So if we had to do more than 30.2, I guess I'll use black so I can show you. So more than 30.2 is going to be just a hair after, that one standard deviation. So right next to it. And more than means you are going, all the way to the right. So that would be this area over here that we would be interested, more than 30.2 pounds. So for this case, our calculation would still be very similar, which means you start out with your z-score first. So 30.2 minus our mean divided by our standard deviation. And what kind of z-score are we looking at here?
1.1.
Yeah, 1.1, because again, like I said, you're just after that first standard deviation. So you can see 1.1 seems like a reasonable z-score. And then based on that, we would need to find its area. So going back to our table here, you are now doing 1.1. And since it is again 0 at because there's no number after 1.1, you still go with 0, and that brings us to 0.8643. So that's an area of 0.8643. But again, guys, remember, this is actually going from, where your 30.2 would be starting and all the way to the left. So all the way to the left is, again, all of this area we're not interested in. That's that yellow, green, orange that we had shaded. We're not interested in any of that. We're interested in that black area, which is shaded to the right-hand side. So that means we will have to, just like I showed you in that generic example, since we're finding what's the probability that our X value is greater than 30.2, or as a z-score, your value is greater than 1.1, you will do 1, which is the entire bell curve, minus the area we got from our table, 0.8643, and whatever that comes out to be is going to be that area for the shaded portion. So 0.1357 as a probability, or again 13.57 as a percentage. And you should be able to verify those numbers. You can see your z-scores here. When we subtracted the two, what your percentage came out to be, or as a probability. For part B, your z-score, and then subtracting that from the 1, what your area comes out to be. Because again, that 8643 is this area here, which we're not interested in. So subtract that from 1, and this shaded area is your 0.1357, or a probability of 13.57. So when you're given these application problems, the first thing would be, draw your bell curve, mark where your shaded area is going to be. So you at least get a visualization of, which area you're looking at. But then step 1 is going to be converting those data values into z-scores. And once you have the z-scores, then based on which area you're looking at, we will have to see, do we need to subtract the 2 z values together like we did in part 1, between 27 and 31? Do you subtract it from 50%? Do you subtract it from 100%? So, that will depend on where your values are going to fall. So it really does depend on each individual example, but, a lot of that framework will stay the same. So again, you will see there's tons of different examples here in your handout to kind of, again, help you find, those probabilities or those areas in here. So let's pick an example from your textbook over here. And again, there's, a lot of good information in your textbook. So I definitely ask you guys to read over it to try and find that. So here in part 7.2, you will see they're giving you some of these generic examples for practice. So again, you can use that just to get comfortable with the bell curve. And then, we can work on some of these application problems. We're probably not going to have a whole lot of time to do these, but, why not? Let's pick Wendy's drive-through. So we can at least get one of these done, and we might have to look at some of these next time. So fast food restaurants spend quite a bit of time, studying the amount of times cars spend in their drive-throughs. Certainly, the faster the cars get through the drive-through, the more opportunity of making money. So QSR magazine studied drive-through times for fast foods and found that Wendy's had the best time, with the mean time spent in the drive-through of 138.5 seconds. Assuming that the drive-through times are normally distributed with a standard deviation of 29 seconds, answer these questions. So let's go ahead and at least create a bell curve for this. And let's see what that will end up looking like. So this is problem number 40 for Wendy's drive-through. Okay, so they're telling us the mean time that the cars had to wait was 138.5 seconds. The standard deviation was 29 seconds. So just based on this, if you had to create your bell curve, can you go ahead and tell me what those numbers for 1, 2, 3 standard deviations above and below the mean would look like? Because again, you would have your 138.5 for the mean time here. And then, of course, you're looking at all those standard deviations with the 29 seconds.
One standard deviation above would be 167.5.
All righty.
2 would be 196.5.
Okay.
And number 3 would be 225.5.
Okay, very good. So above standard deviation. Now, what about below?
1 would be 109.5.
Okay.
2 would be 138. Oh wait, I think sorry. I added it instead of subtracting.
Yeah, the other direction.
Yeah. 2 would be 80.5.
All right, very good.
And 3 would be 51.5.
51.5. All right, perfect. So once we have these numbers, then we can start looking at these questions. So part A is saying, what is the probability that a randomly selected car will get, through the drive-through in less than 100 seconds? So now you can see 100 seconds, of course, is going to be below the mean. Your first standard deviation is at 109.5. The second one is at 80.5. So you know that 100, and they are saying less than 100 seconds. So that's, of course, going to be, somewhere. And again, I'm just kind of eyeballing this, but, somewhere over here, we can say it's going to be 100 seconds and then less than 100. So this is the area we are looking at. So this is less than 100 seconds. So again, we start by finding out what our z-score is going to be. So our waiting time is less than 100. So what do you think the z-score comes out to be? 100 minus your mean divided by the standard deviation.
Negative 19.25.
Yeah, and it is going to be, did you say negative 19? It should be negative 1 because you're between negative 1 and negative 2 standard deviations.
Yeah, it says negative 1.3275.
Dennis, did you just end up dividing by 2 instead of 29?
Yes.
That's what I thought. Yeah. All right, guys. So just to show you the raw answer, it's coming out to be something like this. But since this is a z-score, the maximum you want to do is 2 decimal places. So you have negative 1.327. So that 7 will make the 2 go up to a 3. So you have your z-score of negative 1.33. Once you have the z-score, then you can go to your table, find the negative 1.33. So negative 1.3 is right over here. And then on the top, man, it's not going to let me do it on the same screen. You want to find the other 3. And let's make this guy a little bit smaller. Okay. So negative 1.33, where the 2 of those will meet, is going to be right over here. And as you can see, that number comes out to be 0.0918. So since this is less than, with less than, you don't have to do any calculations because this is 0.0918. And so in this case, you can say, okay, what's the probability that cars wait less than 100 seconds, which comes out to be a z-score of less than negative 1.33, and this is coming out to be 0.0918. So basically, the chance that a car will wait for less than 100 seconds at a Wendy's drive-through has a probability of approximately 9%, right? 9.18. So you can see that's not a very good chance. So more than likely, the car will have to wait more than 100 seconds, but you have a 9% chance that you may wait, less than 100 seconds in the drive-through. And, of course, that can happen on days where you may be the only person in the drive-through, and, if your order is simple enough, they can get it done, pretty quickly. Question on this part over here, guys. We'll have to come back and do the others next time. So on this first part, part A. Okay. So if you have not started working on your homework yet, please get a head start so you at least get a little bit of practice before next class. So that way, if you have any questions, you have a chance to ask me for help. So, all right, guys, we'll stop right here. Sorry about going a little bit over, but I did want to show you that example. So have a wonderful day. Be safe, and I will see you on Wednesday. Take care, guys. Be safe. Bye, everyone.